All right, so what I want you to do first is with your friends at your table, I want you to think about what the word flux means. And then I'm going to ask you. So I'm going to give you just a few minutes here to think about what that means. So I think a good definition for flux is the flow of something through space. So today it's raining and that's really convenient. Let's think about raindrops for a minute. Raindrops are falling, and for the most part we can say that's our something that's flowing through space. Now if I have a bucket and I have it set up here to catch these raindrops. So I have a bucket 1 and bucket 2. What's noticeably different about my two containers? Their size, definitely, and the cross-sectional area. Okay. Which one, bucket 1 or bucket 2, is going to have the most flux, the most flow of something, the flow of rain through the space? Bucket 1. We're going to catch more raindrops with that one. Okay. Now, what about if I have the same raindrops? Well, I have some raindrops here. And then maybe somewhere else, we've got these raindrops. These are the raindrops falling. And I've got bucket 1 and bucket 2. Which one's going to have the most flux? So far, what has flux depended on? The size that can catch it? Maybe. All right. What if I took like a jug? So a jug usually has like a small opening here and then like a wide body there, maybe even a little handle to hold it with or something like that, like a milk jug. So this may have a big body like that one, but which one's going to have more flux? Yeah, 2, because it's not necessarily its volume, but it's what? The size of the opening, the size of the space that can flow through. Okay. So flux depends on the area or the space that it can flow through. It depends on the strength of the stuff, so the amount of stuff. The amount of something. Now, it's still raining, and we're back to a place where we've got constant raindrops everywhere, so we're just, outside and it's raining. And I've got these buckets. One of them is set up like this. One of them is on its side like this. Even put a handle on it so we can see where the bucket is. There we go. And then I have another one that's kind of propped up at a weird like angle thing going on here. Maybe there's a rock under it, under my bucket there. That's a rock. And that's a bucket handle. Which one is going to have the most flux? 1, 2, or 3? 1. What about 2? How much? 0. 3. Some, not the most it could have, and not nothing, but some. So this is the hardest one to come up with the dependency, because definitely you can first say that it's the orientation. So the orientation. Hopefully I spelled that right. If not, you can just fix it. Okay. So specifically, what about the orientation? the definition of a normal line is perpendicular to a plane. So if we let this opening area be the plane, the opening area is the plane, the opening is the plane. If we look at a line that is normal to that plane, that means perpendicular. Normal to that plane, that's perpendicular. Normal to the plane, that's perpendicular. In which case do we have the most flux when our normal is what orientation to our raindrop field when they're parallel? Okay, so we've got the most flux, somewhere in between, and zero flux. What is the angle between this red normal line and the raindrops? 0 degrees. What's the angle between the normal line and these raindrops? 90. What's the angle between the red normal and something that is greater than 0 but less than 90? Is that a decent statement? Okay. When the angle is 0, we have the most flux. When the angle is 90, we have the least flux. Is that a cosine function? Seems like a cosine function. So there's a cosine function there. All right, so let's put all this together. So our flux, the symbol for flux is a phi, capital Phi. It looks like an I with a circle in the middle. We can have electric flux, we have magnetic flux, we can have water flux, anything, really. So it was directly dependent on the amount, the area, and then the orientation, which was the cosine. So B A cosine theta, if we replace our rain with magnetic field. So if flux is BA cos theta, this is our magnetic flux. This is the magnetic field. What's magnetic field measured in? Tesla. This is the cross-sectional area . And what should area be measured in physics? Meters squared, very good. And this is that tricky angle. It's the angle between the normal to the area and the field. So what's the magnetic flux measured in? If you've got magnetic field times area times a ratio which has no unit. Tesla meter squared, which is the same thing as a Weber. Weber. Okay, so from our little experiment, we could see very obviously that if there was a change in magnetic flux that has to happen over time, all change happens over time, then we get an induced EMF. And the symbol for the EMF was like kind of the curly E. And we use that because, mostly for history, but usually that's because it's created by some sort of movement. A voltage created by movement. So this is an induced EMF, which is just your voltage. Now, change in flux. So that means there's a change in BA cos theta. I could change the magnetic field strength by adding more magnets. We saw that the induced EMF must have been greater because we had a greater current. I can't change the area of that particular coil that we were looking at. Now I can change the angle though. Let me show you. So this is a big idea. This is a really important idea. Sometimes you'll see a negative sign in front of this equation. I prefer to find the absolute value and then use Lenz Law to find the direction or the polarity of the induced EMF. So this is our change in magnetic flux. And this is the time. So this would be seconds. This would be Tesla meter squared. So that a Tesla meter squared per second then is voltage. Let's see. So if F is equal to QVB, that means that newtons divided by Coulomb meter per second is a Tesla. I just divided force by the charge and the speed. That gives me what Tesla should be. And a Newton is really a kilogram meter per second squared over Coulomb meter per second. So a meter and a second should cancel out. So we get kilogram per Coulomb seconds. So if I take that, if that's a Tesla, and substitute it in here, we'll have kilogram time meter squared divided by Coulomb seconds. And that has to equal voltage. Oh, divided by seconds gives me seconds squared. And that has to equal our voltage. Voltage is joules per Coulomb. A joule is a Newton times a meter. A Newton is a kilogram meter per second squared, and then times meter. Does that work out? Kind of crazy. You can take a Tesla meter square and divide it by seconds and get voltage. But that is it. My little unit proof. Alright, so if I have a changing magnetic flux, an EMF is induced, a voltage is induced, a current is induced. So let's look at a couple of examples, or a specific example actually. So here is a naked wire, meaning it doesn't have any insulation on it. A naked wire and another naked wire, no insulation. And I'm going to connect these two naked wires by a resistor, a light bulb, whatever, it doesn't matter. Now I'm going to lay a naked bar of metal across those two. Alright, so this is a metal bar. These are metal conducting wires that are uninsulated, so there is a conductive connection between this bar and these wires. And this is a resistor. Now, if I introduce an external magnetic field, that means a magnetic field created by something that's not the bar, the wires, or the resistor. So maybe a bar magnet, something else, an external magnetic field. My favorite one is an into the page magnetic field, X's into the page, X's into the page, X's, X's. Whoops, those are real excited and got together over there. All right, into the page, into the page. Now, this is just boring, sitting there doing nothing, until I give this guy a velocity. What's inside every single thing? Atoms, which have electrons, protons, neutrons. All right, so if I've got a whole bunch of protons or positive charges in this bar and it's moving to the right in a magnetic field directed into the page, then the positive charges get forced where? To the top of that bar. Where do the negative charges go? To the bottom. Negative charges always do opposite of what a positive charge would do. So, this side of my bar becomes positively charged. This side of the bar becomes negatively charged. So we've separated these charges. They really like to get together though. And because we pretend that everything behaves, or we define everything as how a positive charge would behave, is there a path for these positive charges to get to the negative charges over here? Yeah, I kind of gave it away. And if the positive charges, our positive test charges, are going to flow, then what do we have? Current. Boom. There is an induced current in this wacky setup. Why? What am I changing? We have an EMF if we have a change in flux over change in time. That means that we have to change either the magnetic field strength, the area the magnetic field is going through, or the angle of orientation. Are we changing the size or strength of those x's? No way. Are we changing the area by moving the bar to the right? So later it's going to be over here. Are we changing the area that the magnetic field can go through? Oh yeah, we got a delta A there. And cosine of 0, because isn't the magnetic field pointing into the page, and the normal to that plane would either be into the page or out of the page, and that would be 0 or 180, and cosine of 0 or 180 is 1. Okay. And then divided by time. Area. How would we find the area of this thing before and after? Do we need maybe the length of the bar and the distance along the bottom here, D? What's changing, the length of the bar or the distance? The distance. So could I write this as B length, change in distance over change in time? What's change in distance over change in time? Velocity. B, L, V. Mind blown, exploded everywhere awesomeness. So the induced EMF in this type of situation is B, L, V. Sometimes it's called motional EMF because it makes you all emotional. No, I'm kidding. Because it's due to this physical movement of the bar, motional EMF. So this is our EMF measured in voltage. This is our magnetic field in Tesla. This is the length of the bar. And it's in meters. This is the speed of the bar. Now I say speed because we're going to use the direction in our right-hand rule to figure out whether or not the current is clockwise or counterclockwise. So all we need is the amount there. So the speed, which would be in meters per second. So we're going to use right-hand rules to figure out the direction. Specifically, we're going to use something that's called Lenz Law. Lenz Law. All right, so Lenz Law. I like to think of it as the the current induced will create a magnetic field to oppose, is that right? I thought that was strange looking. The current induced will create a magnetic field to oppose the change in magnetic flux. What? Okay. We'll take it one step at a time. So here is a loop, a conductive loop, like the ring hanging from the stand over there. Now, originally, it has no magnetic field in it besides the magnetic field of the Earth, but we can ignore that because it's constant for everybody and it's not changing. So this is before. Afterward, let's say I take a North Pole magnet and point it into it, so I've got into the page. I introduce a magnetic field into the page. Now a current carrying wire creates a magnetic field. So if there's no magnetic field before, the red represents the magnetic field we introduce. And if the current is going to create a magnetic field to oppose, with an O, the magnetic field we introduce, which way should the magnetic field created by the wire be directed? Out of the page. So then what is the direction of the current that runs through that loop? It would run that way down here at the bottom, and then that way, and then that way. So what's that? Counterclockwise. So I'm going to use my hula hoop here to kind of help give you an idea, because this is where you have to think and like reach your hand around behind your page so you can stick your magnetic field fingers out of the page, right? We're all together? Yeah. Okay, so this is the loop. It's just huge. I guess I can make it look smaller if I get away from it. Anyway, but I want to take my right hand rule for the current and the magnetic field around the current carrying wire, reach around behind here, and then grab the loop. So here, so you stick your fingers out of the page and then grab any part of the wire, so you can turn your hand if you need to grab it, but see how my fingertips are still pointing towards you? And grab the wire.
Oh, sorry, I think I missed one part because the thing that access between the page.
Yes.
And then the law says
That the
create a magnetic field to oppose.
So if into the page, what opposes into the page?
Out of the page.
Out of the page.
So the magnet created a magnetic field into the page within the shred loop.
Yes.
And then around the loop, there's one going out of the page.
Yes. The loop will set up a magnetic field out of the page. Grab the wire. It's all due to relative movement. So if you have a positive charge and it's moving in a magnetic field, it is forced. There's a force on it. So what if you have a charge at rest but a moving magnetic field? Would the charge be forced?
Yeah.
It should be.
It
Exactly. So this wire has these charges that are just sitting there. And then when we add the magnetic field to it, it's relative movement, so all the little charges are forced. And so then they start moving, and they are together a current. Let's look at another case here. So let's say that here's our conductive loop, and it starts out with a magnetic field directed out of the page towards you. So this is before it has chickenpox. You don't even know what that is, do you? Y'all have all been inoculated. Thank goodness. Oh. And after, so we're going to remove the magnetic field from this guy. So this one was clockwise current. Yes, I just am backwards. So it was this way, just counterclockwise. All right, so what do you think about this next one? Yeah, so since the initial state is a magnetic field directed out, the wire is going to create a magnetic field directed out to make up for the loss. It makes up for the change, make up for the loss. So we would have a current that was counterclockwise. Now what if we had a region of external magnetic field that was limited to this little square area, and I have a loop, and I'm going to move the loop out of the magnetic field. What's the initial state? Is there a magnetic field inside our loop to begin with? Yes, there's a magnetic field inside the loop. And so as I move it out, what is the wire going to do to oppose the change? The change is losing the magnetic field that's inside. So it's going to create a magnetic field directed into the page inside it. So it's opposing the change. So there would be a magnetic field directed into the page. Grab the wire to get a clockwise current around the loop. So we get a clockwise